In lecture 2 of polynomial ring, we had discussed uh, division algorithm for fx, then remainder theorem, factor theorem, and we have seen the concept of zero of multiplicity, and then we have discussed the fundamental theorem of algebra, and it states that for a non-zero polynomial of degree n over a field has at most n zeros counting multiplicity, and thus this result is not hold if f is not filled. For that we have seen one polynomial in z6 over z6 of degree 2, and it has 4 zeros. So now let us go forward about polynomial ring. So let us recall one definition. We have already seen that definition, but let me recall once again, and this is definition of principal integral domain, PID. So an integral domain D is called PID, principal integral domain. Principal integral domain. If every ideal is principal ideal, if every ideal in D is principal ideal. So that is if I is any ideal in D, and D is what? D is integral domain, implies I is principal ideal, means I is generated by some element for some A belongs to D. And let us recall the definition of A also. See, so this, that is I is what? Ideal generated by A. This means what? It will be of the form A into R, where R belongs to D. So we know that this will be ideal, and it is called ideal generated by A. So if you consider any integral domain, and any ideal of integral domain is generated by a single element, then it is called principal integral domain. So let us see some examples of principal integral domain. Examples of principal integral domain. So say you consider z plus dot, then it is integral domain. Let I be any ideal of z, then I will be of the form n into z for some n belongs to z. So I is what? Nz is nothing but ideal generated by n. Nz is nothing but ideal generated by n for some n belongs to z. So z is what? It is principal integral domain, PID. Now you consider second one. Let f be any field. Let f be any field. Then we know that f has only two ideals, singleton 0, and another is f itself. See, if you consider ideal generated by 0, then it is what? 0 into R, where R belongs to F. So it is what? It is 0, because you multiply any element with 0, then you will get this is 0. So this set contain only 0 element. So singleton 0, this ideal is generated by singleton 0. So I is what? It is singleton 0 is ideal generated by singleton 0. Now you consider ideal generated by 1, and we know that F is a field, so 1 belongs to field contains unity 1. So let us consider ideal generated by 1, then it will be what? 1 into R, where R belongs to F. So it is what? 1 into R. 1 into R is R, where R belongs to F. So it is what? It is simply F. You consider all R such that R in F, so it is F. So F is what? F is ideal generated by 1. So F is what? Ideal generated by 1. So now field has only two ideals, namely singleton 0 and F, and both are generated by single element. So both ideals are principal ideals. So therefore F is PID. So we have this result. So we have this, let us put this thing in a result form. Every field is principal integral domain. So in particular, so therefore we know that Q, R, C, then ZP, then Z3I, Z7I, Z11I. So all these are filled. So all these are principal ideal domain, PID, principal ideal domain. Now let us see one very important result. So this is very important result. Let F be a field. Then Fx is principal integral domain. It is PID. So its proof is very interesting, and it is also easy to understand. So let us see its proof. F is field. See, then we know that Fx is not a field, but Fx is integral domain. So I want to prove that this principal integral of this Fx means integral domain is PID. Means I have to show that every ideal of Fx is generated by some elements of Fx, and notice that the elements of Fx are what? Polynomial over field F. So let F be a field. Be a field. Then we know that Fx is an integral domain. Now let I be any ideal in Fx. So case 1. Suppose I is singleton 0. It is 0 ideal. then what we have? So I is singleton 0. Then as we have discussed previous example or some result, singleton 0 is generated by singleton 0. Ideal singleton 0 is generated by element 0. And case 2, suppose I is equal to fx, ring itself. Then you look at polynomial 1. Now 1 belongs to fx. So you look at ideal generated by 1. So it will be what? 1 into elements of ring. Here ring is fx. So 1 into fx, where fx is in fx. But this set is what? 1 into fx is fx, where fx belongs to fx. So this set is what? All fx. So therefore I, if I is fx, then it is generated by 1. So if you consider I is any ideal in fx, and if I is singleton 0 or I is not equal, I is equal to fx, then it is generated by single element 0 and 1 respectively. Now let us consider case 3. Case 3. Suppose I is not equal to 0 and I is not equal to fx. So therefore I is a non-zero proper ideal of fx. See, it is a proper ideal, so it will not contains unit. So immediate observation, so therefore I does not contains units of fx. See, if I will contains at least one unit element, then it will becomes fx, but our I is not fx, and units of fx are what? Does not contain units of fx, and units of fx are what? Units of fx are constant polynomials. A belongs to f, where f is non-zero element of f. So units of fx, so these are what? Units of fx. We have discussed before. Units of fx are only non-zero constant polynomials. Okay, so now this is my claim. Now I claim this. Now I will prove that this I okay, and before claim let me construct one thing. Okay, so now you consider some polynomial, you consider polynomial, let px be polynomial in I. Now I is non-zero and proper ideal of fx. So now you consider any polynomial in I such that that polynomial should be non-zero polynomial. Now you consider n. N is what? N is what? It is a degree of polynomial px. So n is a natural number, and in I there is no units. So in I there will not be a constant polynomial other than zero polynomial. Zero polynomial is there because I is ideal, so zero element must be there. So zero polynomial is there, but if you consider any non-zero element, non-zero constant polynomial, then it will not be there. If it is there, then that non-zero constant polynomial is unit element of fx, and hence I becomes all fx, but I is not equal to fx. So now you consider all the polynomials. I am going to define one set. Now you consider all the polynomial in I which is non-zero polynomial, then you find out its degree, and let me say that degree is n. Now you consider this n, so you collect n belongs to n such that n is a degree of px, where px is non-zero element of ideal I. Then this set is a subset of n, and n is bounded below this set. It is what? It is bounded below. So this set has minimum of this set exists. Minimum of set exists. So let me say that minimum value of set is k. So what is k? K is the degree of polynomial in I, and that polynomial is non-zero. And if you consider any polynomial in I, then its degree is not smaller than k, because k is the smallest degree of the polynomial, whatever the polynomial in I. Now set of the minimum, sorry, here I did one mistake. K is not this, but minimum of this set is k. So minimum of this set k is exists. So therefore there exists fx belongs to I, such that fx is not equal to 0, such that degree of fx is equal to k. See, minimum of this set exists. It means what? I have one polynomial in I which is non-zero and whose degree is k. So such type of polynomial is not unique. It may be more than one, or it may be infinitely many polynomials in I whose degree is k, but I have considered one. So this fx may not be unique. So now this is my claim. So claim is what? This ideal will be generated by this fx. Now this fx is fixed. Now this my fx is fixed. So now I will prove that my ideal will be generated by fx. So for that I have to prove that I subset ideal generated by fx, and ideal generated by fx is a subset of I have to prove this to inclusion. I is a subset of this one and fx is a subset of this one. I have to prove this thing. So for that, let us start with, let you consider gx belongs to ideal generated by fx. Then how gx look like? So gx will be what? It is fx into alpha x for some alpha x belongs to fx. The element of fx, ideal generated by fx, will be of the form this. Okay, so now fx is an element of I, because fx, we have considered fx, and fx is an element of I, and alpha x is an element of fx, and we know that I is an ideal in fx. So this fx into alpha x will be an element of I, because I is ideal. So but this is nothing but Gx, so implies Gx belongs to I. So it gives me what? Gx belongs to I. So we have considered Gx from ideal generated by Fx, and it is in I, so Fx is a subset of I. So one way is clear. So this inclusion is clear. Now for the reverse part, now you consider, let Gx belongs to I. So then Gx belongs to I, and Fx is a non-zero polynomial. So we can think about, you divide Gx by Fx, means you will get something here and some process and some Rx here. So that is, we will apply division algorithm over Gx and Fx. And notice that what is Fx? Fx is a smallest degree polynomial in I, and that is fixed. So applying so by division algorithm, so let me erase this thing. So applying division algorithm on Gx and Fx, there exists some Qx Rx belongs to Fx such that Gx is equal to Fx into Qx plus Rx. So this is an expression number star. So where this Rx is 0 or degree of Rx is strictly less than degree of Fx, and degree of Fx is what? It is k. Okay, so suppose Rx is not equal to 0. Suppose Rx is not equal to 0, then what we have? Then this degree of Fx let me write exactly. Then degree of Rx will be strictly less than degree of Fx, and it is k. So degree of Rx is strictly less than k. So this is one information. Okay, also from star we have Rx is equal to what? Rx is Gx, you take Fx into Qx to the left hand side, then Gx minus Fx into Gx. So sorry, Fx into Qx. See here, now notice that Fx is an element of I. So all this Fx into Qx will be an element of I. this is will be element of I. Fx is an element of I, so fx into qx will be element of I, and gx is already we have taken from I, and I is an ideal, so all this element is in I. So gx minus fx into qx is in I. So therefore what I have proved, Rx belongs to I, and we have degree of Rx is strictly less than k. So that is what these two things is contradiction, because in I there is no polynomial whose degree is smaller than k other than 0 polynomial, and the degree of 0 polynomial is also not defined, but here I contains a polynomial whose degree is smaller than k. It means that this is not possible. So this is possible only when Rx is 0. So thus Rx must be 0. Rx definitely it is in I, and if Rx is non-zero polynomial, then it is something wrong. So Rx must be 0. So whatever our assumption, suppose Rx is not equal to 0 is not possible. So that is it will arise some contradiction. So Rx must be 0. So if you take Rx is 0, so again from star, so again from star, and star is this one, see, star is this one, Rx is 0, so gx is equal to fx into qx. So gx is equal to fx into qx, where qx belongs to fx. So fx into qx is an element of what? It is element ideal generated by fx. So what we have proved, gx belongs to ideal generated by fx. So therefore gx is any element of I, and now it is a part of this. So hence I is ideal generated by fx. So in any case I will be what? I will be ideal of, if I is an ideal of fx, then I is generated by a single polynomial. So there you mark this observation, mark this thing. See, I is any ideal. Let me summarize this theorem quickly. I be any ideal of fx. If I is singleton 0, then it is generated by singleton 0. If I is fx, then I will be generated by singleton 1. And if I is not singleton 0, not fx, I is any proper ideal, then again I is generated by some polynomial fx. And what is this fx? So fx is a polynomial in I. Fx is in polynomial in I which is non-zero and whose degree is k. And what is k? K is the minimum degree of among the polynomials in I, among the non-zero polynomials in I. So let me show you how we can apply this result. Suppose I have given suppose I is ideal of say Rx, R is field Rx, and let me say let I is not equal to singleton 0, I is not equal to Rx, then what is I? Then what is I? I will be what? So then I will be what? I will be ideal generated by fx, where what is fx? Fx is what? It is a polynomial in, it is a non-zero polynomial in I, and degree of fx is minimum. You choose any minimum degree polynomial from I and you consider ideal generated by fx, then you will get I. So let me put this thing. So ultimately in above result what we have proved, so let me write last line. So thus fx is principal integral domain. So let me prove one, let me state one corollary. Let I be any, not I, let f be any field let I be any ideal, or let me say I be any non-zero ideal of f x. And gx belongs to fx. It is some polynomial. Then this ideal is generated by gx if and only if gx is a non-zero polynomial of minimum degree in I. So we can record the above observation in the form of corollary. So now let us discuss one example. Okay, before going example, let me give one definition. Let R and S be rings. You consider two rings. A function f from a ring R to another ring S is called homomorphism if it satisfies two conditions. First one, f of x plus y should be is equal to f of x plus f of y for all xy belongs to R. See here, this plus is plus of R and this plus is a plus of S, because fx and fy are elements of S. So the addition of fx and fy makes sense if this addition is of S. And similarly, second condition is f of x into y, it should be is equal to fx into f of y for all xy belongs to R. So this into between this into is of multiplication of R, and this multiplication is a multiplication of S. So here f is called homomorphism if it satisfies these two conditions. Now let me define one more definition, and in this case, okay, in if there exists a homomorphism between two rings R and S, then the rings R and S are called homomorphic. Rings. So this is another definition. Now one more definition. Let F is a mapping from R to S be a ring homomorphism. It is a ring homomorphism. Now you consider those elements of ring R belongs to R such that its image under F of R is equal to 0 element of the S. So those element in R which maps to 0. So graphically, so say let this is R and this is S. Here 0, 0, then R1, R2, R3 and some elements, and here 0 element of S, 0 element of, say this is 0 element of R and this is 0 element of S, then S1, S2, S3, S4 and etc. some elements. Now you collect those elements which maps, see definitely 0 maps to 0. It may happen R1 maps to 0, R2 maps to 0, then R4, R5, say R5 maps to 0, but R3 maps to say S2, R4 maps to somewhere else. So you consider those elements which maps to 0 element, this one, this one, this one, this one, etc. So then this set is called kernel of F, as we have defined in the case of group. In group homomorphism we have a kernel of that homomorphism. Here also we have kernel of ring homomorphism. So I leave into the exercise that let F from R to S be a ring homomorphism. Then kernel of F is an ideal in R. It will be ideal of domain set. Next, let me put one theorem, ring homomorphism theorem. Let F from R to S be a ring homomorphism. Then R quotient kernel of F, now it will be able, then you can talk about R quotient kernel of F, then it will be isomorphic to F of R, image of R. It is a similar result as we have seen in the case of group. So let me discuss one example. Now we know that R is a field. So Rx is an integral domain. Now R is a field, so Rx is principal integral domain, PID. Now x square plus 1 is a polynomial in Rx. So let us consider ideal generated by x square plus 1. So now you consider quotient of this, Rx quotient x square plus 1. So then this is what? So this is my question, what is this? Okay, so before going Rx quotient x square plus 1 is what, let me just recall how x square plus 1 look like. X square plus 1 will be what? It will be x square plus 1 into fx, where fx belongs to Rx. Technically ideal generated by x square plus 1 will look like this. Okay, now I want to analyze this structure, how it look like, or it is exactly what. So for that you consider a map. F is a mapping from Rx to set of complex numbers, and you define F. Let me use the notation for mapping, not F, but let me use, say it is, say, phi. So phi of fx. Fx is an element of Rx, it is of some polynomial. So now you evaluate the value of the polynomial at I, then it becomes a complex number. So phi of fx is equal to fi. So you define map in this way. So see, let me illustrate this map, so how it looks. So for example phi of x cube plus 7x plus 8 will be what? So it is x cube plus 7x plus 8 at x is equal to I. So that is what? I cube plus 7i plus 8. I cube is what? Minus I plus 7i plus 8. That is what? 8 plus 6i. So it is some complex number. So phi of fx is equal to fi. So now my claim is this: phi is a ring homomorphism. So for that, let fx and gx belongs to Rx, then phi of fx plus gx will be what? Phi of f plus g at x, but that is what? F plus g at I, but it is f of I plus g of I, and this is nothing but phi of fx plus phi of gx. So phi of fx plus gx is phi fx plus phi gx, and second condition phi of fx into gx, and that is nothing but phi of f into g at x, but this is fg at I, and that is nothing but fi into gi, and this can be written as phi of fx into phi of gx. So therefore phi is a ring homomorphism. Now you look at the kernel of phi. So kernel of phi will be those polynomial in Rx such that phi of fx is 0 element of C, and 0 element of C is usual 0. Okay, so as we have discussed above, and you will prove it, kernel of phi will be the ideal in Rx. So now kernel of phi will be what? It is an ideal of what? Ideal of Rx, and we know that Rx is what? PID. So kernel of phi will be generated by single element, say tx for some tx belongs to Rx. Now my question is that what should be this tx? What should be this polynomial tx? So in the proof of the theorem that fx is PID, we have discussed any ideal, any non-zero proper ideal of fx is nothing but it is generated by a polynomial of the from the I whose degree is the smallest. So here kernel of phi and here kernel of phi is what? Fx belongs to Rx, so that phi of fx is equal to 0. So let me write one more step. So here kernel of phi will be what? Fx belongs to Rx, such that phi of fx means f of I is equal to 0. So those elements, those polynomials in Rx such that its value at I is 0 means I is the 0 of the polynomial. So so if you consider any let ax plus b belongs to Rx and a is non-zero polynomial, a is not equal to 0, and let me say it is fx, then f of I will be what? F of I will be ai plus b, and a is non-zero, so this number is never 0, as a is not equal to 0, right? So you will not get any 1 degree polynomial in Rx whose root is I or whose 0 is I. So now you consider let fx is equal to x square plus 1, then f of I will be what? I square plus 1, and it is minus 1 plus 1, and it is 0. So fx belongs to Rx, fx is equal to x square plus 1, which is polynomial in Rx whose such that f of I equal to 0, and it is what? It is the smallest degree polynomial. So therefore smallest degree of the smallest degree of or let me write in this way, therefore the degree of small therefore the degree of smallest degree polynomial in I is equal to 2, because 1 degree polynomial will not be in I. 1 degree polynomial will not be in the kernel. So let me write the smallest degree, the degree of the smallest degree polynomial in not I, in kernel of phi is equal to 2, and it is what? X square plus 1. So therefore kernel of phi will be what? It will be generated by x square plus 1. You may have some another polynomial also, but x square plus 1 will work. So kernel of phi will be generated by x square plus 1, because kernel of phi is ideal of Rx. Rx is principal integral domain. It is generated by single polynomial, and question is what is that polynomial? Then that polynomial is x square plus 1, because x square plus 1 is the smallest degree polynomial in kernel phi. So now by ring homomorphism theorem, and which is that I have just stated that theorem, this one, let f from R to S, this theorem, be a ring homomorphism, then R quotient kernel of f is isomorphic to f of R. So now by ring homomorphism theorem, and which is that theorem, this one, let f from R to S, this theorem, be a ring homomorphism, then R quotient kernel of f is isomorphic to f of R. So now by ring homomorphism theorem, and which is that theorem, this one, let f from R to S, this theorem, be a ring homomorphism, then R quotient kernel of f is isomorphic to f of R. So Okay, before applying this theorem, let me prove one thing. Now second claim, phi is onto. So for that, what we have to consider? You consider let alpha, or let alpha plus I beta belongs to C. Now you find out a polynomial, then find say some px belongs to rx such that phi of px is equal to alpha plus I beta. So I will put into the exercise. So you find this polynomial. So definitely you will get this polynomial, and it is very easy exercise. So I assume that phi is onto. So by therefore so finally, thus by ring homomorphism theorem, Rx quotient kernel of phi is isomorphic to phi of Rx, but phi is onto, so implies phi of Rx will be what? It is C. So this is what? It is C. So therefore this Rx quotient kernel of phi, but kernel of phi is x square plus 1, it will be isomorphic to C. So Rx quotient x square plus 1 will be isomorphic to C. See, later on, to analyze such type of structure, we will use some another powerful results, and using that powerful results, we can skip all these calculations. And but that we will discuss later on in some lectures. But to understand or to digest the concept of ring theory, we have to at least go at least once through this type of arguments, and it may be helpful somewhere else. So here we stop this lecture. Thank you.